Can you mute mic 2, please?
You get first place in trivia, you will win this very nice poster of Kepler 16b in honor of our exoplanet talk. So if you want to come play trivia, come grab a sheet and a pencil to participate. And if you're an astronomer, you can participate, but you won't get prizes.
I think I have that one already.
I've seen some professors right now.
Just a couple of minutes now. As a reminder, if you'd like to participate in the astronomy trivia for our astronomy tap talks, please come up here, touch the really big, giant, bright screen to get a sheet and a pencil. And if you're in the back and you can't hear me, can you please wave? Awesome. Thank you. We're going to get started here in just a few minutes.
Those mics should be off until the moment someone with mic on speaker. Yeah. So for the actual trivia, you should have my mic on so that people online that can participate. because we sit right next to the microphone, you should be a little cautious about what you say. But that way, yeah, it's not a problem.
All right. Well, now that we're all set up, I'm going to do my brief introduction before we start trivia. Welcome to Astronomy on
Tap number 103. Woo! And thank you to the wonderful Scoot Brewing for hosting us. Today we'll be hearing from Nick Tusay on Disintegrating Exoplanets and Habitable Worlds, and Jake Kurlander on Asteroid Discovery with the Rubin Observatory. And our next meeting will tentatively be February 18th at a yet-to-be-disclosed location. And without further ado, we'll begin the trivia. So, question 1. What causes some exoplanets to disintegrate? It's a very relevant question for one of our talks. Is it A, stellar winds stripping material? B, collisions with moons? C, nuclear reactions in their core? Or D, impacts from comets? There will be 10 questions. I'll give you a minute on this first run through, and then I'll go back through them really quickly afterwards.
But not ambiguous. There are two you would say. At the bar trivia level. Welcome to the question. Oh, I got a friend showing up. That's like a serious consequence. Thanks so much.
No way. Well, I mean, I guess it depends on your definition.
All right, question 2. Disintegrating exoplanets are most often found very close to their star. Why? Is it A, that's where strong gravity is? B, that's where there's extreme tidal forces and heat? C, there are more frequent asteroid impacts? Or D, there are faster orbital speeds? What is the main reason disintegrating exoplanets are most often found very close to their star?
Is this one clear answer?
Yeah, the problem is that like, all of these are true.
But only one of them is why.
Right.
If one of them was lost. It sounds like two is.
Question 3. Which type of planet is the most likely to disintegrate? Is it A, gas giant, B, ice giant, C, rocky planets, or D, ocean worlds?
That's really interesting.
Yeah, I mean, it really depends on the it's kind of a niche.
Oh, sure, right?
Question 4. What is the habitable zone around a star? Is it A, where the planets form, B, where liquid water can exist on a surface, C, where planets can have atmospheres, or D, where life has been detected?
It's true.
Average or score. Oh, wow.
I'll be going over this in my talk.
Called this movie a long time ago with Dr. Dre,
So that they could be educational, like
San Francisco police test. They went to the police test. All the way down, like, yeah, whatever.
Question 5. Why does a planet's atmosphere matter for habitability? A, it controls the planet's color. B, it protects against meteorites. C, it regulates temperature and radiation. Or D, it increases gravity. Aren't two of these perfect?
He doesn't like Dr. Dre, and he's just like constantly berating him.
It's not the new one.
And then Dr. Dre is just totally like low status character in that situation, and he's like plays it so well. It's so hilarious. It's crazy.
Question 6. What single feature of Rubin Observatory enables discovery of moving objects so efficiently? Is it A, adaptive optics, B, an extremely wide field of view, C, infrared detectors, or D, spectroscopic survey mode?
That sounds crazy. Adopting to me.
I always forget to active because one that was
Actually about this. She's like,
Valerie was close, but she has spent the last 3 days not doing anything.
Question 7. What makes Rubin's camera unique among optical telescopes? Is it A, a built-in coronagraph, B, gigapixel scale detector, D, cryogenic infrared sensors, or D, an adaptive secondary mirror?
if I were to like write a sci-fi, I'll just like put all these.
It totally sounds like the made up stuff in Star Trek. Yeah.
We would never make things up.
Information, and I think adaptive.
Just reverse polarity into coronagraph.
repolarize the power electric.
Exactly.
Yeah.
Which is their top to reboot it.
Exactly, right?
Question 8. Why is difference imaging critical for Rubin's asteroid discovery pipeline? Does it A, improve photometric calibration, B, remove atmospheric distortions, C, isolates moving objects from static backgrounds, or D, measures asteroid colors? Wow, reflection. Cool.
I mean, not close, but like it's one thing.
That's sick. You have 3 credit cards. Question 9. What is a tracklet in Rubin asteroid discovery? Is it A, a full orbital solution, B, a single detection of an object, C, a short sequence of detections in one night, or D, a simulated asteroid?
They're minor. They went to the asteroid. They're on the way back or something. Right. Told to stop off. Was there always a mission, or if they were like?
And finally, question 10. What limits Rubin's ability to detect very small asteroids? Is it A, atmospheric turbulence, B, telescope mirror size, C, object brightness and trailing, or D, computer processing speed? after this question, I'm going to go back through them real quick so you can lock in your final answers.
I hope I'm going to see this.
Really say much more than just like. That's a thing.
That sounds awesome.
We don't need it.
Exactly.
Just some space observatories on the ground.
If we didn't have an atmosphere. We need to get rid of the atmosphere.
All right, now I'm going to go back through the questions real quick just to make sure you got all of that down and all the answers you need. That wasn't going back through them though, that was quick.
Physicists against the habit.
But I'm only going to read them once. Now you just have to look.
Astronomers against all atmospheres.
Your answer and my answer on this one is I'm not entirely clear on that, but it's basically the same thing. Two, what causes them to disintegrate rather than speed? And I feel like they go so fast because of that. So how is that different? How are they? It's like almost the same answer. Okay.
This is the most exciting part of the talk where I stare at my watch for 3 minutes.
Let me go. Here we are. Yes, we are. Gotta. I'll be excited if I get to it.
I'm going back through them.
Oh no, yes.
I was going to say that.
He's such a good series. It's such good. Do you get the spoons?
No, your speech were donated by Megan.
Have you seen the new Proximity?
There's any blood?
Yeah. It's awesome. I got it at the light. I don't know how it works. New to me.
This is your astronomy trivia. If you please come up to the front and return your sheets and pencils, please. We will grade them during our first talk, and then we will get back to you right afterwards. While we collect your sheets, we're going to quick switch over to our next talk, and then we'll get started shortly. Thank you so much.
Right. That's the idea. Yeah, let's.
Then you can do that if you just like.
Let you presenter view. Perfect.
Stuff like might be happening. There's an observatory on the UW campus,
And then the mic should work.
Once you're ready,
Do I need to do that? You did that.
I think it might happen. Just kind of hoping that it's perfect. Really, this is the thing that's not just one of the things on the website. Is this Tuesday? Oh, that's Atlanta. Not Tuesday.
So what's going to happen is that you're going to want to unmute me soon, and I'm going to introduce you. I'm going to hand the mic over to him, and unmute him.
So my son in college, he has a girlfriend.
So while I'm introducing him, it should just be like camera view, and then as soon as he starts talking, we'll switch to slides.
There's a very, very long time ago, I was at some sort of like convention or something, and there was some people who were like, want to measure gravity waves, and that sounds pretty cool. We're going to take satellites, drop them in outer space, and we're going to put them a long way from each other and shoot lasers at each other. It's kind of like,
In astronomy trivia, it is now my pleasure to introduce our first speaker for tonight, Nick Tusay, who's currently a postdoctoral scholar at the University of Washington and got his PhD at Pennsylvania State University, also known as Penn State for those of you in the know, in astronomy and astrophysics and astrobiology. Give it up.
All right, can you all hear me? Great. All right, this is exciting. So I am here tonight to share with you some of the research that I've been doing on disintegrating exoplanets. But before I get into some of the cool and exciting results that I have to share with you, I want to take a step back and start with some motivation and some context for what I'm going to share with you, hence the habitable world. So to start with, how many planets do we know of currently with life on it? That is correct. Just one. We currently know of one planet with life on it right now. And it is teeming with life. And until about 30 years ago, a little bit more than 30 years ago, we really only knew of the planets in our solar system. However many you want to count, let's not talk about Pluto. So the first discovery of exoplanets happened in the mid-90s. And since then, it's gone gangbusters, this field of exoplanets. And we now know of over 6,000 exoplanets. That is 6,000 planets outside of our own solar system. That is a lot of worlds on which to consider where life might be. But the question remains, which of these planets, or even the ones that we haven't discovered, have life on them? Which of them are habitable? And in the 2040s, hopefully, but probably later, don't hold your breath, we will be launching the Habitable Worlds Observatory. This is NASA's next big flagship mission to look for exactly what it says in the title, habitable worlds. But the question then becomes, what is a habitable world? And I'm obligated to show you this plot, which basically describes the habitable zone around a star. So for a given star size, there is a distance at which liquid water could persist on the surface of a planet. And NASA's motto in finding life outside of our own world is follow the water. So when we go looking for habitable worlds, we want to look in the habitable zone where water could persist on a planet. And that habitable zone is not too close to the star so that the planet gets too hot, like Venus, and not too far away from the star so that it gets too cold, like Mars. You want something in the Goldilocks zone, like Earth. And that's all well and good, but in reality, it's way more complicated than that. There are a lot of different factors that go into habitability. There's the geosphere, the biosphere, the atmosphere, the magnetosphere. All of these systems are very complicated on their own and intricately connected, tied together, and it's really difficult to disentangle what are the most important parts that go into determining what makes a world habitable. And to make matters worse, our actual measurements of exoplanets aren't that great. We know that they exist, and we do have measurements on a lot of them. And they're actually really precise for what they are. But if you can see these lines extending through these dots, that is the uncertainty on these measurements, right? So and this is for terrestrial sized worlds. So the uncertainties on the mass and the radius of the worlds that we know of that are terrestrial sized, rocky worlds like the Earth, Venus, Mars, those kinds of size of planets, the uncertainties on them are larger than we would like them to be. And all this really gets you is a bulk density. Mass and radius tells you density, but the density of a planet can mean a lot of different things. The interiors of planets have a significant impact on the atmospheres that they can hold on to, the evolution of the possible land that might be on that planet. And so it's really important to understand what's going on the interior of that planet, not just with bulk density, but the actual composition. The problem there, of course, is, as I like to say, planets like to keep their insides on the inside. And that makes observing the insides of planets really difficult. But that is where disintegrating exoplanets comes in. Because disintegrating exoplanets are actually exposing their insides on the outside. And so we can measure the starlight passing through the effluents that used to be these planets' interior and hope to measure the composition of these worlds. And that's really exciting. Now, how do we do this? This is done, generally speaking, with the transit method. The transit method is the most popular way of detecting exoplanets and also measuring their composition. The atmospheric composition usually, but in our case it's special. So this happens when a planet is aligned, where a system is aligned fortuitously such that from our point of view, the planet passes in front of its host star. When it does, if we can accurately measure the brightness of the star, sometimes we'll see a dip in that brightness. That is called a transit. The planet passes in front of the star, the light from the star dips, and we can measure the depth, and we can tell how big that planet is, depending on how precisely we measure. There's a lot of caveats there, and it's really difficult to do, but it's very doable, and this is actually how we've discovered the vast majority of the exoplanets we know of today. And the fancy thing you can do with that is you can then take that light and break it up into a spectrum, like passing that light through a prism to make a beautiful rainbow. And you can measure the different depths at the different wavelengths that you measure, and that'll tell you the different sizes of that planet. Now, that might not make sense, because how does a planet change sizes? Well, the body of the planet, of course, is not, but what you're actually measuring is the atmosphere around that planet, right? Normally. I'll get to disintegrating planets in a second. But normally, for transiting exoplanets, we're measuring the atmosphere, or the light passing through the atmosphere, and depending on the composition, right, it'll seem bigger or smaller based on what wavelengths are blocked out by certain molecules. And we can then take that, those different depth measurements, and plot them up in a spectrum. So we measure the depths at different wavelengths, we plot it up, and then we compare that to laboratory measurements. We take materials that we expect to be in that atmosphere, or in our case, a disintegrating exoplanet cloud, We measure that in the lab when we say, okay, at a certain wavelength, it will absorb this much light. And then we measure, and then we compare that against what we actually measured for our exoplanet. That's cool. That's great. And that's the idea. Right? Our disintegrating exoplanet is a special case. It's not an atmosphere around a planet per se. It is the light passing through the effluents coming off of the planet that was once its interior. All right. So backing up again, just a second, just to refresh your memory here, this is what the cartoon picture of a transit looks like on the left. And on the right, this is actual data from the Kepler Space Telescope of a transit light curve. This is what we see when we point a telescope at a normally behaving transiting system. We see the flux from the star that we normalize to 1, and we say we can measure the brightness of the star very precisely. And then we see these tendrils coming down from the brightness of the star. These are all those transits. When you zoom into one of them, you see that familiar U-shaped pattern. Looks all great and good. And the reason that I show you this and illustrate this to you is so that you can compare to this. This is K2-22b. You may notice that its transit light curve looks significantly different from the one that we just saw. The star's flux is normalized to 1, and it does have long tendrils hanging down from it, and those are indeed transits. The period of the transit is shown by these teal marks up at the top. But something weird is going on, right? There's quite a bit of variation in the depth of the light, in the depth of each transit. In fact, sometimes it doesn't look like there's any transit at all. That's weird. What the heck is going on here? And additionally, some of you have read that this thing orbits in 9 hours. That means the year for this planet happens twice a day. That's really close to its host star. So, all of these pieces of evidence point to the fact that this is a disintegrating exoplanet. And in fact, what we're seeing is not the exoplanet itself, but something more ephemeral that can come and go on a very short time scale, like the cloud coming off of a disintegrating exoplanet. That might come off the exoplanet, blow away, not be there sometimes, be there in higher density other times, and so we get this variability. And this is the basic theory behind disintegrating exoplanets. The planet itself is so close to its host star that the surface rock, there's no longer an atmosphere, there's just the surface rock is sublimating off. That means it's going directly from solid rock to gas because it's so hot. It's launching off into space towards the star because it's going right from rock to vapor and just launching off the surface. And then it contacts the stellar wind, and that blows the effluents off into these tails. Some of it is able to survive that radiation pressure and proceed into a closer in orbit, which then creates a leading tail. But most of it is actually blown off into a further orbit, which produces a trailing tail. And I just want to highlight for you that the size of this planet is not to scale, but the distance between this planet and this star actually is. And you never see that in these kinds of plots. This planet is actually really, really tiny. It's basically, you can't see it, like it's smaller than a pixel here, but it is actually this far away from its host star. If the star is this big, then this planet is actually this far away from its host star. 3 stellar radii away from its host star. That's really close. Now, so I gave you the picture of how this works. It's basically just radiative heating that makes that catastrophically evaporates the surface. It is not being tidally ripped apart. It's not gravity that's doing the ripping apart. It's just being bombarded with so much radiation that it's just melting off. Cool. So, this is a really cool target, and so what we did was we put in a JWST proposal to observe this in the infrared, because we want to study the dust. We want to know what the components of the dust cloud are. And dust has a lot of really interesting features in the infrared. And infrared is notoriously difficult to do from the ground, which is exactly why JWST was built to go into space and study things in infrared. This picture is actually an image from the data that we got. I want to note that this is a binary system. You're not seeing the planet there. That is the host star and its companion, which is about 500 AU away. Not very important. But that is the actual star, that big one. That's cool. And that is JWST. So, we observed this thing in 2024. We got 4 transits, about 20 hours on the telescope. We calculated from that K2 light curve that because of the variability, we need multiple transits in order to secure a viable transit depth, right? Sometimes it's just not there, so we need to make sure that we're going to get it. And so statistically, we found that with 4 transits, we had more than a 95% confidence that we would get at least 0.5% cumulative depth. And 0.5 was the threshold that we came up with for being able to distinguish between the different components in the spectrum. And so we went with 4. We got 2 independent transits, not linked to each other, and then 2 more in a full phase curve. That is, we just stared at the star until the planet went all the way around. So basically, we just stared at it for about 11 hours, right? And if it's a 9-hour orbit, it just went around, and we got 2 transits in there. So we got 4 total transits that way. We also tried to get some simultaneous optical coverage. Not really important. I don't really have time to go into that. Don't worry about it. You can ask me about it later if you want. But let me tell you about the data that we got. So, JWST did its thing. They don't let us touch it, but they do let us tell us where to point, which is nice. And then they give us the data. And so I looked at the data, and the first transit looked like this. To the untrained eye, this might look like there is no discernible transit, and you are right. There's nothing here. But, you know, to be expected, this thing is highly variable, not a big deal. We have 3 other transits. Let's look at the second one. Well, that's unfortunate. There's nothing in the second one either. Okay, well, you know what? These were the 2 independent transits. We still have a full phase curve to look at. Surely there's going to be something good in there. This is where I started to panic, because my PhD thesis was riding on this. The first half of the full phase curve shows no significant transit. Oof. Luckily, the 4th transit does show a measurable depth. So we did get it, and I did graduate, and I am a doctor. Woo! I'm just kidding. They probably would have passed me anyway. Anyway, unfortunately, this was only about 0.16% depth. And as I noted before, we were hoping for, well, we were expecting, really, based on the statistics that we had gathered, that we would get at least 0.5%. We were super confident that we would get way more than 0.5%. But we only got 0.16%. But it's still enough. It's still enough to do something. So we fit a model to the transit light curve. We also did the same to the Cheops data. Again, not really important. It's just an optical component that we were trying to leverage at the same time. Again, I can go into that later if somebody is really that curious. But the highlight is the JWST data, so let's focus on that. So I took that model, and for every channel, or every wavelength in the spectrum, I fit that model to every wavelength. And I said, how deep is it in each channel? Just like I tried to show you before. And from this, I was able to produce the first spectrum of the transiting effluence of a disintegrating planet around a main sequence star. I think that qualification is right. Here it is. Binned up with a constant spectral resolution of 17 and a pretty rainbow color pattern. The uncertainties are unfortunately a little higher than we would have liked, but we can say something from this. So the idea here, right, is the spectrum is pretty, and that's all great and good, but ultimately, we want to know what that spectrum is made of, right? We want to know what the constituents of this disintegrating world are made of. And so going into this, we had a suite of solid dust models. I'm showing you here just a sample of those that we expected to see based on Earth mineralogy, right? We know what the Earth is made of. We know what terrestrial planets in general should be maybe made of. That's kind of what we're testing. So we wanted to see, is this made of the same stuff? Unfortunately, like I said, the uncertainties are a little high, so it's really difficult to make any definitive conclusions. But we can say a few things. First of all, we think that these wiggles and bumps are real. We don't think that this is statistical aberration and it's just a flat line, which is good. A flat line could mean nothing at all. Could mean it's completely opaque and we don't know what we're looking at. Or it could mean that it is just iron. If you take the Earth and you strip off the core, and then, if you take the Earth and you strip off the crust, and then you strip off the mantle, you're left with just the iron core, right? And if you start melting that off, you just see a bunch of iron species. And in this wavelength range, iron species generally present as flat. And we don't think it's flat. So we don't think that this planet is down to its bare core, if it has a core. Mantle, however, is a little bit more difficult to discern. It is consistent with a lot of the mantle species we look at, so that's pretty much all we can really say there. It's consistent with certain things that we expect to find. But the keen-eyed among you may have noticed I have yet to say anything about this feature here. At about 5 microns, we have 2 points that go from super transparent to very opaque. And all of our solid dust models cut right through them. And that doesn't make any sense. So what's going on there? Well, it was at this point that our team realized that we had forgotten to take into account gas. Which, obviously, there should be gas if the rock is turning directly into gas and then dust. So there should be a mixture of dust and gas. What could it be? Well, in the literature, it suggests that if you are melting things like Mg2SiO4 or Fe2SiO4 or MgSiO3 or things like that that you find in the mantle, you should see some gases like MgO and SiO. Long story short, our data are not consistent with that, which is weird. So what does that mean? Not my problem. Okay, so what we did find was we looked at other gases from other planetary bodies that we know of, like icy bodies around the solar system, like Pluto and comets and things of that nature. And weirdly, NO and CO2 seem to line up. The referees would have a field day if I tried to claim that we definitively detected this after saying that we can't definitively detect certain mantle species. So all I can say is that it seems consistent, but honestly, we have no idea at this point. What we really need to do, as any good astronomer will tell you, is go back and look at it again. So, here are my conclusions. It was a really exciting project. We can say some things. It wasn't as gangbusters as we had hoped, as we expected, and the reason for that is totally not our fault. Ask me why later, but it had nothing to do with us or the instrument. It was totally interestingly astrophysical in nature that is actually so missing. And that is the state of things, but wait, there's more. So, the reason that we chose K222b is because it was one of 3 disintegrating exoplanets found with Kepler. We knew of 3 at the time, and this was the brightest and best target, for sure. And we thought, yeah, this is the one. Let's do this. And if you want to go back and look at the others, they're just not as good to look at. So what we really need is a better target. And until about 1.5 years ago, we did not have one. But now we do. This is BD05. It's actually BD plus 054868AB, whatever. We call it BD05. This was found with TESS. It was predicted that TESS would find a lot of these, and so far it's found one. But this one is amazing. This star that this planet is around has 100 times more flux than K222. It is significantly brighter. If you're into magnitudes, K222 is Vmag of 15, this is Vmag of 10. It is super bright. It saturates a lot of things, not JWC. And so we wanted to look at it with JWC. This is all plots from the Discovery paper, published about a year ago. This shows you why this system is really cool. One thing you can notice is that one thing you can notice from the TESS light curve, is that the transits never go away. Unlike K222b, the transits never go away. And so there's no worry about the problem of, I gotta get a lot of transits because I don't know if I'm actually gonna see this thing. And the transits are really deep, and you get this sharp tooth pattern that is indicative of these things. And what's really cool is that for more than 50% of the orbit, the tails are there. That's incredible. And so we took JWC and we stared at this thing too. We took those observations in October. We are currently still analyzing them, and I am going to share with you unpublished, never before seen results. So you're getting a sneak peek at things that other scientists haven't seen. No pictures. Don't steal my scoop. Right, so here we go. This is what we see. So we got a full phase curve. This one actually orbits, I think, in 1.27 days, which is like 30-something hours. So we got about 40 hours on this target. So we got a full phase curve with 2 transits again. And what you'll notice, some of you, is that the shape is a little bit different, isn't it? It doesn't have that distinct sharp tooth pattern. It looks a little bit more symmetrical in these transits. Well, that's weird. Especially when you compare it to the TESS light curve, right? The TESS light curve looks like this. JWC looks like this. So what is going on? Barbara, I said no pictures. I'm just kidding. You're fine. You're fine. So it might elucidate things when I plot it up like this. What many of you might have noticed is that the depth is actually different in both of them. In infrared, it is significantly shallower, and we're probing through a lot of that dust, which should make sense to those of you who are keen on infrared. The whole idea of JWC was to peer through all of the dust that we are often blocked by, which is what infrared is good at. And so we see through a lot of the dust, and we see a lot less structure, and the main body of the transit is hidden right there. And so that's really cool. And this is a animation that I put together of a very preliminary look at the spectrum of the transits as they evolve over time. Again, I can't stress enough that this is preliminary. And my model is different than my collaborators, so things could change. It looks pretty similar, but not quite the same. And I'm sorry to leave you on a cliffhanger, but the science is still in progress, so that is unfortunately the state of things. So, that's it. Cool. Oh, nice. Good. Any questions? How are we doing? We're just asking questions? What's up?
Moons of a planet effectively how much sunlight gets reflected back rather than just the planet itself, how much gets detected in maybe like when the planet is in our line of sight, it's going to block more light than if it's between the planet and the star.
So can the moons of a planet affect how much light? Yeah, that's what I'm doing. Thank you. So can the moons of a planet affect how much light we see from a transiting planet, basically? And the answer is, in general, yes. However, not in these systems. In a system like this, it's so close to its star, there's no planet, there's no moon. There's just no way for it to exist. But in a lot of transiting systems, people do look for moons. The problem is that, generally speaking, moons tend to be a lot smaller than planets, and we have a hard time detecting planets, and so it's really difficult to detect moons. We have a couple of candidates, but it depends on who you ask whether or not that's something you even want to bring up. So the answer is it should, but how much is debatable. Good question.
How fast is this 9-hour thing going? It's just like,
How fast is this 9-hour thing going? Well, so if it's 9 hours and it's 3 stellar radii away, you can do the math. I can't do it in my head, but I've done it before, and I don't know, some amount of kilometers per second. It's very fast. But yeah, it's zipping around. Yeah, it's very fast, but it's also very close in. So that's how you get it.
I guess how much distance is that in our solar system? Is that like
So in terms of our solar system, it is 45 times closer to its host star than Mercury is to the sun. 45 times. That's K222b. BDO5 is a little bit further out, but not by much. So K222 is around an M0 star. This is around a mid-K star. They're not that much. They're not that different in size. But yeah, it's really close. Any other questions? No, this is not a habitable planet. But we are hoping that by understanding the composition of planets like this, we can discern the habitability of other worlds. Going once? Going twice? All right. Thanks, everybody.
Problems halfway solved. Let's give Nick another hand. That was great. And now it is everyone's favorite part of Astronomy on Tap. It is the trivia answers. So I'm going to read the answers, and then I'll let you know which team won our grand prize. So question 1 asked, what causes some planets to disintegrate? The main way is through stellar winds stripping material off of these planets. Question 2, disintegrating exoplanets are most often found very close to their star. Why is this? That is because that is where you find the most extreme tidal forces and the most extreme heat around the star. Question 3, which type of planet is most likely to disintegrate? It is a rocky planet, C. The other types are not nearly close enough to do that, and also are harder to. No, I'm getting bad looks. I don't do planets. I should stop guessing things about planets.
They're different. They're just different.
They're different, Nick says. Awesome. Question 4. What is the habitable zone around a star? That is where liquid water can exist on a surface.
Yeah.
Good, good, good.
You do need an atmosphere, but that's fine.
Question 5. Why does a planet's atmosphere matter for habitability? It is mainly because it regulates the temperature and radiation, although some of the other ones are also true, but don't matter for habitability. Question 6. What single feature of Rubin Observatory enables discovery of moving objects so efficiently? This is B, an extremely wide field of view. It looks at a lot at once. Question 7. These are a little bit of spoilers for our next talk, so get ready for that. Question 7. What makes Rubin's camera unique among optical telescopes? This is its gigapixel scale detector, the highest resolution camera ever built, I believe. Very impressive. Question 8. Why is difference imaging critical for Rubin's asteroid discovery pipeline? This is because it isolates moving objects from static backgrounds, and you may hear more about this soon. Question 9. What is a tracklet in Rubin asteroid discovery? A tracklet is a short sequence of detections in one night that can help you pinpoint an asteroid. And question 10. What limits Rubin's ability to detect very small asteroids? This is object brightness and trailing. It is hard to detect things that are not bright. And so, the moment you've all been waiting for, we have other prizes. We have other prizes. Okay, awesome. In second place, with 8 correct, is Team Jason on the Red Giant. And got every single question correct. 10 right is Team Singularity. Congratulations. If you are one of our lucky winners tonight, please come up to receive a prize during our intermission. We are going to switch over real quick to our next speaker. We're going to take about 5 minutes to take a break, and then we'll get right back into more science. Thank you all. Uh-oh. Hmm.
Right train.
Green beans go.
All right. It should only be another couple minutes. Thank you all so much for your patience. We're really sorry about this. This has never happened to us before. So we are currently doing our best to move the slides over to a computer that likes this projector, and then we should be able to project it. Thanks again for your patience.
Hey, all right. You're welcome. Go get them. We got this.
Thanks again so much for your patience.
We've circumvented our problems, let's say that. So it is now my great pleasure to introduce Jake Kurlander, who is a fourth-year graduate student at the University of Washington Astronomy program that I'm also a part of, and he's also an organizer of Astronomy on Tap and has done great things for this organization, so please give him a big hand.
Thank you, Sam. All right, hi everyone. I'm Jake, graduate student at the University of Washington, just like Sam said. My PhD thesis is on using the Rubin Observatory, giant survey telescope in Chile, which is going to conduct a 10-year survey, the LSST, to find as many asteroids as we possibly can and use them to learn whatever we can about the solar system. All right. I will refer to the Rubin Observatory and LSST by both of those names back and forth during this presentation. Same thing. I hope to answer 4 questions for you tonight. First, what is the Rubin Observatory? For anyone who has not heard dozens and dozens of times the start of this talk from different people, many of whom are in this room. The second, how will the Rubin Observatory discover millions of asteroids over the next 10 years? Only 1.5 million are known today, and I claim it's going to discover another 4 million over the next few years. Question 3, what has Rubin done so far? What data has it taken? What have we learned from that data? And 4, what will it discover next? What can you look forward to over the coming days and weeks and months and years? All right, we'll start off with question number 1. What is the Rubin Observatory? Rubin Observatory is a giant survey telescope with an 8.4 meter primary mirror on Cerro Pachon, a mountain in Chile near La Serena. It is an incredible telescope, an incredible instrument that's been under construction for almost 20 years now, and it has 4 primary science goals at which it's going to do the best of any instrument ever built. First, to discover as many asteroids as possible, to conduct an inventory of our solar system. 2, to discover as many supernova as possible, which allows us to constrain the expansion rate of the universe and measure this mysterious thing called dark energy. Number 3, to map the Milky Way out as deeply as possible, to discover tens of billions of stars, and help us map our galactic structure. And finally, to map the large-scale structure of the universe, for all of the images at the end of the survey to be added together to create a single, giant, the deepest possible map of the southern sky ever built. So why can Rubin do this? What makes this telescope in Chile, that's just barely started operations, special? The answer is a strange French word, étendue. It's the product of the size of your primary mirror, the area that can collect photons from the night sky, and the telescope's field of view in square degrees. So here's Rubin, LSST, sitting at 10 square degrees of field of view and an 8-meter primary mirror. In the product of those 2 things, the total light collecting capacity of the system, it beats all other observatories and even the next few observatories put together. It's not quite bigger than every other dot on the screen put together, but it's way up there. I'm a big data guy. I love solving computer problems, math problems. If you care about big data, the Rubin Observatory is going to collect more data, more photons than any other instrument. There are other survey telescopes that take very large pictures. That's up on this chart, like ZTF, Pan-STARRS, Atlas, but no other ones are built at the largest scale of telescope we can build, 8 to 10 meter. Rubin first was talked about in the mid-90s as the dark energy telescope. Folks figured out that the universe is expanding at an accelerating rate, driven by something that we don't understand very well called dark energy, and wanted to build a giant wide-field survey telescope to find as many supernova as possible. In 1998, just before I was born, a sketch of the unique 3-mirror design was put down by the folks whose faces are right there at the bottom. And in 2003, the LSST Corporation, a group of people working together to design and propose this instrument, came together. In 2004, they received $14 million from the National Science Foundation to plan this, and they also signed a contract to build the primary mirror. In 2006, the site at Cerro Pachon was chosen, and in 2008, the giant slab of glass that became the primary mirror was first revealed. These are people. That's the 8-meter primary mirror. It's absolutely huge. In 2010, the American Astronomical Society ranked it as the top priority for the next decade to build the Rubin Observatory. And in 2014, the National Science Foundation allocated about $500 million to actually construct the whole thing. From there, the floodgates opened, instruments were built, the mirrors were covered and polished, and then in the 2020s, after some COVID delays, the mirrors and the instruments were all sent to the site, now constructed on Cerro Pachon, and the Rubin Observatory has been finishing its construction over the last year or 2. On April 15th of 2025, the first full images were taken. Rubin first light, and ever since it has been in commissioning. Here is some video from one of those first nights of the Rubin Observatory taking pictures of the night sky. It's real, it exists, we have data. You'll notice it's not moving very quickly. It's supposed to eventually survey the whole night sky over and over again very quickly, but for the first few months, it's been pointing pretty steadily at individual regions of the night sky so that we don't move it too fast and break the very expensive 10-year to build mirror. But it's real. This is such a nice video. Okay, that's the Rubin Observatory. How will it discover millions of new asteroids? Why am I confidently saying that it will do that? The Rubin Observatory has a really unique cadence. Here we see a single night of observation simulated by some wonderful folks on the survey strategy team. This is how it tiles the sky with its 10 square degree field of view, covering over and over again, or covering as much area of the sky as it possibly can twice in a night. So you'll see it completes covering one small region of the sky and then goes back to the start, fills it out a second time. When it changes colors, those are changes in the optical filter that's in front of the camera, which lets us get a 6-color view of the night sky. That's one day. You just saw one day of nighttime observation, covering a reasonable fraction of the sky twice. Traditionally, a telescope that wants to discover asteroids will take 4 pictures in the same spot every night. And if there's a moving object, it's moving slowly in those pictures, it's pretty easy to pick out 4 dots next to each other, 1 moving object, 1 new asteroid. Now, because supernova are such an important part of Rubin's mission, and the supernova people do not want to return to the same spot 4 times a night, they want their observations more spread out, Rubin has decided to take 2 pictures each night. But 2 is really different from 4 if you're trying to draw straight lines through points that are near each other. Every 2 points near each other could be a straight line, and so Rubin can no longer discover a new object with a single night of data. Instead, actually quite recently in 2018, some real clever folks came up with an algorithm called HelioLink, which allows you to take a bunch of low confidence tracklets, just 2 points, propagate them all to the same time, and look for clusters of objects, clusters of tracklets that are high confidence multi-night detections of low confidence single night detections. So if you get 3 of these tracklets that appear in a curve that looks just like an orbit, that probably is a real new asteroid. So we've got a simulated survey. Folks have decided how this telescope is going to take pictures of the night sky. And we have a discovery mechanism, HelioLink. If you put those 2 things together, you can simulate a 10-year LSST survey against a model solar system, state-of-the-art model, and produce a simulated discovery catalog. So this, the blue dot there is the Earth going around the solar system. A simulated Rubin Observatory is sitting on that blue dot. And you are watching in real time as the simulated observatory discovers new asteroids. In the very center, we've got some red objects, the near-Earth objects. These things occasionally hit Earth. One of them killed the dinosaurs. And we would like to not be the dinosaurs. So Rubin is hoping to discover at least 90% of the 140-meter or larger near-Earth asteroids. Keep us safe. The gold ring, that's the main belt. That's where almost all of the 1.5 million known objects, currently known today objects, live. Main belt is dominated by collisions between different objects. So almost all of these objects are small and fragments of other objects that collided in the past. Here in the lavender, we've got the 2 Jupiter Trojan clouds. These are objects that used to live much further out. They used to be icy, but they were sent in and somehow got captured at the L4 and L5 Lagrange points of Jupiter. They're an incredible resource if you want to study the materials of the outer solar system much, much closer to Earth. And then finally out here, we've got the Kuiper Belt. These are the primordial icy bodies that are left over from the formation of our planets in the very early solar system. They still have most of their ices. So if you're interested in how planets form, how Earth got all of its water, and you want to understand in other solar systems what sort of planets we should expect, the Kuiper Belt is the right place to study. It is very well preserved from the start of the solar system to today, and it's where most of the planetesimals, most of the building blocks that didn't make it into a real planet, live. All of the theories about Planet 9 are derived from patterns in the Kuiper Belt that we see. And the claim that Rubin is going to answer the question of Planet 9, whether it exists or not, is the claim that it will measure the Kuiper Belt very, very well, discovering tens of thousands of Kuiper Belt objects. All right. Rubin Observatory is an awesome telescope. It is going to discover millions and millions of new asteroids. What has it done so far? April 15th, 2025 was a while ago now. It has taken some images, and in those images, we have found some asteroids. Here are some videos from Rubin First Look, 7 days of observation in late April 2025, and there are new asteroids. These, you'll notice there are a lot more than 2 pictures in a night, so you get these nice clean motions. They weren't moving the mount too fast. Yeah, multiple in some of these in a beautiful galaxy. All right, on night 1, about 1,000 new asteroids. And by the end of night 7, about 2,000 new asteroids. It's very, very exciting. There's a lot of them. Almost all of these are regular main belt asteroids. The main belt is way easier to see than anywhere else in the solar system, and it's full of these 100-meter, 1-kilometer asteroids. But we also got some Kuiper Belt objects way out there and some near-Earth objects in the middle. Now, it's not typical that we would take so many pictures in the same spot over and over again. But doing so meant that these first objects we discovered were very, very well measured. Now, asteroids aren't perfect spheres. They have some shapes, and they're also not perfectly still. They tend to rotate at different speeds. And a lot of work has gone into measuring the rotation speeds and the shapes of different asteroids. One of the 2,000 found in Rubin First Look, 2025 MN45, appears to be not spherical in that its brightness changes over time. We believe, well, some wonderful researchers at the University of Washington believe they have found the rotation period of this asteroid at 1.88 minutes. Now that's really fast. The fastest sort of asteroid you typically see has a period of about 2 hours. Some of them spin about as fast as 1 rotation every 2 hours, and that's the speed at which, for a rocky body, if it weren't one solid body, it would spin itself apart. So you can imagine there's some pull of gravity in, you're sitting on the surface, you're orbiting at some speed. Your speed will be escape velocity if your average asteroid is rotating once per 2.2 hours. And there's a couple discoveries of interesting objects that seem to have periodic variability in the brightness faster than 2.2 hours, but certainly none nearly as fast as 1.88 minutes, and certainly no 700-meter objects. This is a nearly kilometer-sized object spinning once every 2 minutes. It is unique among asteroids that have been observed and understood, and there isn't like an easy answer about why it's like that. It seems strange that you could have a collision between kilometer-sized objects and end up with a single solid 700-meter chunk that's stuck together. That collision might leave one of them spinning pretty darn fast, and so collisions are the main culprit for why this object is so large and spinning so fast. But current models of collision physics shouldn't lead us to have found 2 or 3 objects in the first 2,000 we looked at that were this large and spinning this fast. And so there's some unsolved mysteries of asteroid collisions that are being revealed by these first objects. All right, Rubin has a plan for how it's going to survey the sky. And then over the last year, it has taken a bunch of test images over the sky. In blue, we have the number of visits per night in the simulated baseline survey case. So blue is what we would like to do for full survey operations eventually. Orange is what we have done this year, number of visits per night. So we're currently at about 20% survey speed, which is totally fine. Commissioning takes a while. There's a lot of things to get right. But there's a big chunk in late June and early July where we were at really high image density, and we were actually doing this in a Rubin survey cadence-like way. 2 visits per night, covering a reasonable fraction of the sky. So we've got, while not full-scale Rubin survey, a pretty good first step for it. And running HelioLink on this data we found some additional asteroids post for Rubin first look. I should say Rubin first look is like this. And so all of the oranges is all of the images we have taken so far. Okay. Number of asteroids we've discovered so far. One green dot is 1,000 known asteroids. Green is 1,000 asteroids. A green dot is an asteroid that was known before Rubin that we rediscovered in a blind search. A white or light green asteroid is an unknown one. We've got about 90,000 known asteroids rediscovered by Rubin and 30,000 candidates for 3-night new discoveries. Now, I would love to show you pictures, but unfortunately all of the pixels are under embargo, and my boss is here, so I really can't show you all of the pixels. But this is what most of these candidates look like. 2 dots one night, 2 dots a second night, 2 dots a third night. But we're finding something a little tricky in a bunch of our data. Among those 90,000 known asteroids rediscovered were 500 asteroids that are really 2 nights of one known asteroid and 1 night of another known asteroid. These are mixed linkages. And these are really, really tricky. And in almost all of these cases, all 3 nights of data for both asteroids were there. And it just so happens that these alignments of different asteroids that are relatively common look perfectly as if the wrong tracklet lines up with the other 2 tracklets. So if we add in the mixed linkages, we've got about 1 per 100 mixed linkages in our 3-night data. 1 per 100 is a lot. We really don't want, for 1% of the asteroids we discover, to not be real asteroids. For one, it's really hard to go back and change them. We can go back and change them, but it's just a real hassle. For 2, if someone writes a scientific paper like these ones about these really exciting new spinning asteroids that spin much faster and are much larger than previous superfast rotators, it would really be tough if someone were to write a science paper about one of these asteroids and it turns out, oh, that was 2 asteroids together that looked real. So we'd like to get this down. Our internal benchmark, we'd like to get below 1 per 10,000 fake. Currently in our 3-night data, we're at 1 per 100. Now if we split it up by the number of nights these objects have been observed, almost all of the mixed ones are 3-night linkages. And we've also got a bunch of 4-night linkages. About 40% of our linkages, the new candidate asteroids, were observed on at least 4 nights. And of the 500 mixed linkages, 499 of them were 3-night linkages, and 1 of them was a 4-night linkage. So among the known asteroids that we've observed on at least 4 nights, we've got a mixed linkage rate of about 1 in 40,000, which satisfies our 1 in 10,000 purity requirement. Now, if we split the unknown asteroids up into the 3-nighters and the 4-nighters, that leaves about 12 or 14,000 new 4-night asteroids, each of which we are 99.99% confident is a real asteroid, as opposed to these 3-nighters that we're only 99% confident. So that's the answer. We've got somewhere over 10,000 new 4-night linkages. These have been sitting around in a file that should get submitted to the Minor Planet Center for verification and official discovery. We've been working out some issues in the system for submitting them, but I've heard that tomorrow is the day. Been told these 10,000 asteroids, 14,000 asteroids should get submitted tomorrow. All right, that is what Rubin has done so far. We've done a little bit of survey-like data collection, discovered a bunch of new asteroids. We've done a little bit of non-traditional deep drilling data collection and found some really cool things about a couple of asteroids, a couple of thousands of asteroids. What's coming next? Okay, first the fun thing. In 2006, a spacecraft called New Horizons was launched out to explore the outer planets in the Kuiper Belt, and it took incredible photos of Pluto. I believe this is a composite of a few of the different photos it took of Pluto. It got really close to one cold classical Kuiper Belt object and found that it was bilobed. There were like 2 objects stuck together. Totally changed what we think about how planets form and provided a lot of support for a really cool idea called the streaming instability that I don't have time to get into now, but New Horizons did some really amazing things for planetary science. It passed Pluto in 2019-ish, and now it's just heading out of the solar system. It will leave our solar system. But right now, it's still inside our solar system. And it would be really, really cool if we could find another target that happens to be in its path for it to pass in the next couple of years before it runs out of fuel and before it's so far away that it can't really course correct. It also just so happens that in April and May, when first light was happening, that the New Horizons field, where this spacecraft right now is on the sky, was really conveniently located for us to observe and satisfied a lot of the things that we were looking for in a test field, like moderate stellar density and low air mass. And so 360 images were taken in different filters, right centered on where New Horizons is right now, as it's leaving our solar system. Now, none of those images had like bright new Kuiper Belt objects that just popped right out, and the field's been searched very deeply by Subaru before Arrokoth, before the Pluto flyby. But with 300 new images, you can use a newer asteroid discovery mechanism called shift and stack. So the idea is, if you have one picture of a Kuiper Belt object that's very, very dim, you cannot see that object in your picture. If you have 300 pictures of an object, you can just sum them up, stack them on top of each other, and faint things become bright, and your signal to noise improves as the square root of your number of images, and so you should be able to see something about 19 times fainter in 360 images than you could in one. Now, shift and stack is tough for asteroids because the asteroids move. Well, sorry, stacking is tough for asteroids because the asteroids move. Instead, you have to do shift and stack, where you correctly guess the asteroid's path on the sky and shift all of your images so that the asteroid, this imaginary asteroid you're trying to find, sits at the same place in all of those images. And if you can correctly guess that there is an asteroid on a certain orbit in your image, and then you shift all of the images so that that asteroid is in the same place and sum them up, then you will see it about 19 times brighter than you would if you were just looking at one image. So there are some folks at the University of Washington taking the 360 images of the New Horizons field that Rubin took and shifting and stacking them all sorts of ways and trying to find new things. We don't have results yet, and we don't know when we will have results, but the possibility of finding new distant objects in this field is super, super cool and is one of the only examples of like coordinated astronomy, Earth to space, like trying to save a space mission, get another lap in before it's out of the solar system. So this is, a lot of work is going into this at the University of Washington, led by some wonderful folks, including Colin Chandler and Dino and a bunch of the KB mod folks. All right, that's the fun, exciting, crazy idea. If you're interested in the normal, boring, standard 4 million new asteroids over 10 years, the Rubin survey of LSST, this line item, February or March 2026 should start in the next couple of months. Exact date has not been set yet, but in the next couple of months, we're going to start the LSST, observe for 10 years straight, and find millions of new asteroids. They'll be announced each night as they're discovered automatically by our daytime solar system discovery pipelines. And the new detections of known objects will be announced within 2 minutes of shutter close through the alert stream. So if you really want live updates, go find the Rubin alert stream. Okay, I'm going to leave you with some conclusions here and take any questions you've got. Number one, we found 14,000 new 4-night asteroids in SV data. We have a bunch more 3-night candidates that we are pretty confident but not confident enough to announce, that hopefully we'll get more data for and rescue. There are some record-setting discoveries from the very dense observation period of Rubin First Look. The real survey is going to start sometime in the next few months, and millions, hopefully 2.2 million images and 4 million new asteroids will be discovered. Fingers really, really crossed. All right, thank you, everyone. Okay, any question?
How do you determine the x-axis of an asteroid's position? You get the single track, where it is, like how far away.
How far? Oh, so the along track. Yeah. So when you see an asteroid, how do you know how far away it is? That is a very good question, and that is the question answered here. In a single night of motion, you get an asteroid's angle, so 2 parameters, where it is on the unit sphere, and its angular rate, which way it's moving on the unit sphere. The 2 things you don't know are how far away it is and its velocity along your line of sight. The really clever trick in the heliolink algorithm is to search over those parameters. So you get a list of every distance and velocity an object could have, and you propagate those. That gives you, for each low confidence tracklet, a full orbital solution. You propagate those all to one time, and if 3 tracklets have exactly the same orbital solution under your guess, then that's a new object. And it works really well. There are some cool degeneracies that actually make it work way better than it should. You don't have to guess all that many distances and radial velocities in order to search quite completely. But maybe the more intuitive answer is the curvature of this line. So this gives you 4 parameters, then you measure 2 more from the curve over the next 2 tracklets. Any other questions? Yes?
How frequently do you have to observe a certain period of an asteroid before you confirm that's what it's doing?
That it's rotating at a certain frequency? Yeah. Yeah. How many observations do you need of an asteroid to get its rotation period? Rotation period or orbit? Rotation period. Okay. Yeah. So there were 2,104 new asteroids discovered in Rubin first look, and the average one had about 200 detections, 200 data points. It had been seen 200 times. Out of those 2,000, 76 had rotation periods that were fit. So not a huge fraction, 3%, I think. That implies that you should need more than 200 detections. But even among the ones with 400 or more detections, there was still not a very high rate of recovering orbital periods. The big reason for that is that you can only tell an asteroid's rotation period from its light curve if it is non-spherical enough that you see substantial fluctuations in its brightness. Like if you looked at a perfect sphere, it doesn't matter how fast it's rotating, it's always reflecting the same amount of light back to you, and so you're never going to see it, its rotation period. So the answer is a couple hundred if it's elongated enough to have a substantial light curve. If it doesn't have a substantial light curve, there's nothing you can do. And the question about in the middle, the detection efficiency, is the subject of a paper by Alex Fleming that went on the archive in mid-November that I recommend you read if you're interested in learning a lot more about the answer to that question. Then, yeah.
Rubin may discover 4 million new asteroids in the next 10 years.
Yeah.
What's kind of the error bar on that?
What's the error bar on the number of new asteroids that Rubin's going to detect in the next 10 years? That's a really good question. The parameter that encodes that is the size distribution of the main belt past where current surveys have observed it well. That is not, we're definitely discovering a lot more asteroids. Like looking at the Rubin images so far, they're largely a little more blurry than they're going to be in the long term, and we're still finding new asteroids at like a 1 to 3 rate, 3 known objects per 1 new object. That's definitely going to get past 1 to 1. We expect it to get up to 3 to 1 from 1 to 3. If it were only a doubling, if it were only 1.5 million new asteroids, I would be very, very surprised. I think a couple million is the lower end estimate. Now, in general, size distributions really, really consistently throughout astronomy, throughout asteroid science in particular, people expect there to be more small objects than there are. And this was the subject of a bunch of really good papers in the early 2000s, including a Hubble deep stack, doing shift and stack for asteroids with Hubble in 2004 by Gary Bernstein and Matt Hallman, and the TAUS transit, looking for transits of stars by asteroids. And both of them found like a 20-time reduction in the number of distant small objects that we think there are. So there's a lot of historical precedent for overestimating these numbers. In the main belt case, I think we know it pretty well. It'll be a few million new. Yeah. And then new algorithms like shift and stack for the main belt could open that up a little further as well. Okay, any other questions? I'll also be around after the talk if anyone wants to chat. Yeah.
Can you talk about our government's scrubbing of data to hide certain satellites?
Can I talk about our government's scrubbing of the data to hide certain satellites? We are not supposed to, and we are going to not discover anything that orbits the Earth. So there are cuts we make to our input data to make sure we don't find anything in Earth orbit. It's a pretty simple cut. I think I'm not allowed to say the number though. So we make, if something's moving fast enough, we throw it out. There's a first-year graduate student, Ian Chow, who's working on using the really fast-moving things to find objects that are about to hit the Earth. And there's a lot of really cool science we can do looking at like the 1-meter-sized objects that are right on close approach. And almost all of those, we've done some really cool survey simulation with the same system as showed that cool circle video before. Almost none of those objects will be filtered out by the satellite filter. So pretty separable. Yeah. All right, well, thank you all very much. I'm still Jake. I will be up here if anyone wants to chat more about Rubin and asteroids and big data. Otherwise, thank you all so much for coming to our talks. This has been wonderful. Yeah.
Thank you all again so much for coming. Let's give our speakers another round of applause. All right. Well, our next Astronomy on Tap will likely be, I had it in my head and then I forgot, February 18th. I hope to see you all there. We will let you know where it will be shortly. And yeah, thanks to our speakers. Thank you all so much for coming. Have a nice night. Get home safely.